Hello, everyone. Hope you're doing well. Let's talk a little bit more about this type of arguments that we introduced in the 6.1.4 video lecture. Let's just talk a little bit more about what's going on here with the diagonalization argument. What does it mean? Let's kind of break apart the different parts of the definition and theorem first before we move on. Now, some of you may have already kind of gotten the gist of what you need of the diagonalization theorem from the first go over on it. Maybe you've seen similar theorems before, or you're kind of used to some of those layerings of theorems. But this is one of the proofs that has the most layers to it that we're going to be seeing again and again. So that's something that I want us to start taking a look at here. Now, some of our major theorems from this week are going to use this diagonalization type of argument. So that's my main reason for highlighting this. This is not something that we are going to be asked to recreate word for word on any type of assignment. But this is for your own enrichment to see what kinds of arguments you might see if you keep going down this particular route, whether it be analytical, applied, or if it be theoretical, or even if you're just going to be reading in this direction for fun someday. This is a type of argument that you will see over and over again. One of my colleagues who is now a postdoc he is in Poland now, he told me that the way that you know that you understand analysis is that you understand how to diagonalize, that you can take something and figure out how to wrap this into a diagonalization argument to make it say what you want to say. And we'll see how this kind of works here with this definition and theorem combo as we go through this video. First, let's start with the definition. A function f from s to t for two subsets s and t of the real numbers is a contraction if the function f is differentiable and the absolute value of its derivative is less than or equal to 1 for all x in S. A way to think about a contraction is that its growth is controlled by 1. Some of you may know that this is actually a one way to think of if you're looking at the space of differentiable functions. This is kind of looking at a Lipschitz continuous function where your value of m in that definition is equal to 1, or perhaps even less than 1. However, Lipschitz continuous functions aren't necessarily differentiable in and of themselves, so this isn't a if and only if between the two definitions. But that is one way to think about this, is that you can have a function that is essentially growing or shrinking only by a certain rate, right? So you can have something that looks like this, but you can see kind of why I'm trying to draw the picture this way. The amount in which it's allowed to grow or shrink is very limited. If you try and draw something of slope 2, then that is not allowed because that would be a place where the slopes of the tangent lines of that function would be greater than 1. So that any part of that in the function cannot be allowed. You cannot have the function grow quickly or shrink quickly at any point. It's going to only be able to go and be differentiable for where the absolute value of that derivative is less than or equal to 1. So let's take a look here at the theorem. Let's let S be the set of all contractions starting with the set 0 to 1. Now, I went ahead and highlighted what this codomain is going to be, but actually this is automatic. If you have a contraction going from 0 to 1, and you know that your function value starts at 0, then we actually know that this is the only way that you can get a y value out of a function, is if that y value is somewhere in between -1 and 1. Think about this for a little bit. This is a function that has to start when x is 0, it has to be at 0. So think about how quickly this function could grow or shrink in order to get to its final endpoint over here to 1. There are two ways that I can imagine it trying to get to the extremal properties of how high or how low its y value could go. First, remember that we can't have a function go very high because at some point its slope is going to be greater than 1 at that point, and it ceases to be a contraction. So, and remember that means that at every point, the slope of this derivative, the slope of this function, slopes of tangent lines of this function, must be less than or equal to 1. Well, that means that the largest possible growth that you can have for this function is the line of slope 1. Everything else has to kind of dip down at some point or even out or even just decelerate its growth a bit. This line of slope 1 is going to have a top point of 1, 1. And it's also going to have by a similar notion, we can also say that this contractions can only go down by the path of a slope of -1 at its steepest. Any other contraction can live only inside of this little swath right here, right? This is the steepest that it could possibly go at any given point, and any other function that you might draw here, because of the fact that the functions are limited in their growth at every single point, there's no way for a function to be able to escape this swath of the blue line that I have going up and the green line that I have going down. So the values that I have here are going to be the y values that are possible in this function are those that go from -1 to 1. There's no way to make it go anywhere outside of this range. So I put in -1 to 1 just to mention that that is following actually from the fact that these are contractions that all start at the point where their x value of 0 is equal to 0. Then we're actually making a claim here that this set here, S, is a compact set in the set of continuous functions with a domain of 0 to 1. Let's go through and recall what we're using here as our definitions for compact here. We say that a set S, a subset of a metric space X, is compact if every sequence in S, and by in S we mean with elements inside of the set S, has a subsequence that converges in S. So let's think about this for a second. One way to remember this is that Bolzano-Weierstrass in the real numbers is saying exactly this, which says that if you take a bounded and a closed set inside of there, then you're going to be able to take sequences that have convergent subsequences in there. So that's the whole idea behind working in Bolzano-Weierstrass, those types of theorems. If you want to remember what that is, go back to section 2.4 to take a look at that. So compactness is saying that sequences in these kinds of what we are imagining as closed and bounded sets, although now we know that there is this kind of stretch, we have to add a little bit to bounded to make this work in a metric space and talk about something called totally bounded to make this work. That if we have this sort of compact set, then we can start analyzing this in terms of sequences, that every sequence that has elements inside of the set has a subsequence that converges inside of that set. So let's recall also what it means for a sequence to converge inside of this set. Well, first, all of these are functions in and of themselves. So we would say that f sub n, the sequence, converges to a function f inside of the space of continuous functions with a domain going from 0 to 1 if, and this is by definition, we say that a sequence converges to the function f if this primum for all x inside of the domain, the absolute value of the distance between the function elements, sequence elements evaluated at this point x, minus the function f itself evaluated at this point x, goes towards 0. This is because this is what is meant by the distance between the sequence elements f sub n and f, is that you take a supremum of the absolute value of the difference of each of the valuations of this function here. Now notice that this is a sequence of functions f sub n, but when you isolate out, taking a look at these values here, when you plug in a value of x for a function, what you get out is a sequence of numbers. So even though f sub n is a sequence of functions, which is eventually what we want to show has a subsequence that converges in S, something that we're going to use a lot to make this happen is that we will say that whenever you plug in an x value, that what you get is a sequence of numbers. So when we plug in a number like x equals 1/2 or x equals 1 for this, then what we are doing is we are looking at those functions here and we are saying, okay, well, the function value is the y value of the function at that point. And if I have a sequence of functions that's continuing to do something here, then the sequence that I'm looking at say, f sub n of 1/2 here would be something like this. It would be just the y values corresponding to that particular x value for each of those sequence of functions. As I continue to push n up, I do get a different function, But what f sub n of 1/2 is looking for is just the y value of that function when x is equal to 1/2. So let's go through and see how we can start working through this theorem. Now, our goal is to show this definition is true. A set S of a subset of X is compact if every sequence in S has a subsequence that converges inside of S. So here is how we're going to have to start with this proof. We're going to have to start with let f sub n be a sequence in S. Now, what that means is each f sub n is a contraction, and each one goes from 0, 1 to -1, 1, such that f of 0 is equal to 0 for all n in the natural numbers. So that's to kind of get us an idea of what these functions are doing. What might these functions look like? We are not given anything about this sequence converging outright. Namely, the functions that we might be getting here might look something a little bit like this, where it doesn't even seem like that the functions have any sort of order or anything to them as far as how they might be converging. In fact, you can imagine kind of how I'm working through and graphing these functions here. What I'm doing is taking a few functions and just kind of filling up the space a little bit. And maybe even I break up the rhythm some more and I add in a few functions in the middle of some of the other functions that have already been defined. These are all functions that are contractions, meaning their growth is going to be limited, going from one place to another. But I know nothing about the sequence of functions other than it's just a sequence of functions of contractions. But I do know something else, and you can see it here because I've already drawn it here with the picture where we were marked on this first. I do know that the functions themselves are completely contained within this little triangle. They are defined from 0 to 1, which tells us kind of the height of this triangle going from left to right. And then they are also going to be bounded by the base on this bottom, on this right-hand side, how low they can go and how high they can go for these functions. So an interesting question that we might ask is, what is the distance between any two functions inside of this? We'll go through and start by making a quick claim here. And this is more just, we don't actually need this at this point for the proof, but I'd like to show this as a way of kind of explaining what steps we're going to be taking here. But for the claim here is this: for all n in the natural numbers, the distance, and m as well, the distance between any two function values or any two functions here with respect to the infinity metric that we use for the continuous functions, the distance between those two is less than or equal to 2. And how do we see that claim? Remember that the d infinity metric that we're talking about is exactly this function. It is the supremum for all x values of the difference in y values at a given x value. Well, taking a look at this picture, if I had two functions inside of this little triangle here, what would be the largest possible distance between those two functions? Well, the truth is that the way that I'm drawing the functions may be a little misleading. Sometimes that supremum is still going to be not at the very far end of the functions, but it might actually be somewhere in the middle, somewhere inside where this might be perhaps where that supremum is taken. Kind of thinking again of the maximum distance between two functions. But either way, whether my supremum takes place in the middle of this interval or even at the very end, I do know that the largest possible distance that they can possibly have between them happens here at the very end. The largest possible distance between y values is 2. If the supremum happens to happen over here and this end, well, then their supremum is just going to be less than 2. It doesn't break the fact that our highest possible distance between the two functions is going to be 2. In fact, there's no way that you could go greater, because otherwise it would be escaping this triangle somehow. So that tells us a little bit about what we're looking at. Now, that doesn't mean that this is a Cauchy sequence. A Cauchy sequence, remember, means that if you take these two separate function values, f sub n, f sub m, and have them go off and their distance be smaller and smaller as you continue to cut off finite values at the beginning of the sequence, then you can say it's a Cauchy sequence, and then perhaps we could get something that converges from that, since we know the space of continuous functions is complete. So what are we going to do then? So how are we going to figure out how this works. We want to find a subsequence of the sequence of functions f sub n that does end up converging. So what we're going to do is we're going to start by making some candidates for some subsequences. Let's start here. I'm going to first figure something out. I'm going to do this as claim 1, and then I'm going to keep going with claim 2. Consider the sequence f sub n 1. Now remember that just like we were talking about from before, this sequence is the sequence of numbers where I plugged in x equals 1 for each of the functions, and I'm looking at their corresponding y values now. So now I'm considering this sequence. Now, a reason I might want to consider this sequence is just when I was looking back at this picture here, I noticed that the largest possible distance was going to be out here at when x is equal to 1. So maybe I want to study that a little more and see what I can come up with for that. So let's consider the sequence of f sub n of 1. Now, here's how we're going to do this. F sub n of 1, this sequence, we know from what we've just been discussing that wherever the values of this function land, they have to be within inside of the codomain of the function, which is inside of -1 to 1. We've talked about why that is, that they have to be in between -1 and 1, and that's because they have to fit inside that triangle. But something else to notice is that this is a compact set in the real numbers. Now we have a sequence f sub n of 1 that has a compact set in the real numbers. So here's what we're doing. We're starting to leverage the fact that we want a convergent sequence of functions, and hence to show that this function is compact. And what we're doing to be able to do that is leveraging other compact sets to make that happen, like the codomain of this set, which we can start putting function values in because of we can just plug in a value in for the function and get out a y value, which happens to be inside of this compact set. So there is a subsequence, and we'll call it f sub nk of 1, or actually, I'll call it f sub nk of the sequence f sub n, such that the sequence of numbers f sub nk of 1, that this sequence of numbers converges. Now, this is all by definition of compact. So this is the definition of compactness of the set to 1, 1, -1, 1. Because the fact that is that f sub n of 1 is a sequence of numbers inside of this closed interval going from -1 to 1. So what we're doing is we're choosing a subsequence of that. Well, here is that little index there for that subsequence. It's the n, which is there for the functions. So in fact, by changing that index to give me a subsequence, I'm actually finding what ends up being a subsequence of functions, f sub n sub k. Now, that tells us that the sequence of numbers converges. So let's take a look at what's happening now. At this point, we are having the function values converge to a particular point. Oops, bring that back. Let's have them converge to right here, for example. So that means that, let's say that we are past a certain point in which the point at which we are converging is within epsilon. So you can now see what these functions might look like in order for them to be converging to a point inside of this space of contractions. Notice how all of these functions look. Now, some of you might be thinking, okay, well, John, you're telling the narrative how you want it here, because it looks like all of these functions are a lot closer than the ones that you've got from before. But let's talk about why that's actually the case. There's actually, once again, a farthest possible boundary that you can be able to reach using the limitations of a contraction. All of the functions that we have, if they are going to converge exactly to this point or have exactly this function value, this little rectangle that I've drawn in red here is where those function values can be. They can only be inside of that little red box. If they're going to have exactly that function value, that's all that they can be. Now, we may be outside of some sort of particular epsilon, so maybe we have to add that in a little bit by adding a bit of a dotted kind of expansion there for what kinds of functions are allowed. But other than this, this is telling us that in order to satisfy the rules of a contraction, a function has to live inside of this dotted box. Think if I had a function that went all the way down here, how is it going to have a function value of that point? Well, at some point, it would have to jump all the way back up, but that breaks the rules of a function being a contraction. So what that means is that now that we've shown that past a certain cutoff point, that this subsequence here can actually be really, really close at this point of this point of f sub 1, this value in which these values at x equals 1 are converging, what we're seeing now is that these functions are now banding closer and closer together. This particular subsequence that we found has distances between functions that are much closer than the others that were much farther apart. So let's just make a quick note to that. Note the distance between functions f sub nk seems a lot closer than those of f sub n, which is a pretty cool fact. It seems like we're actually getting closer to this by forming a subsequence. So something tells us that maybe we should be repeating this process from one subsequence to the next. That is, we have shown that these points continue to get closer at the value of x equals 1. What if we did this again at another point at which these functions seem to be pretty far apart? Maybe we just take this rectangle and divide it in half. Think about what would happen if I said not only do the functions have to converge at x equals 1 for a particular subsequence, which is true, we know, by the definition of compactness of the open interval from -1 to 1. But what if we could repeat that process again for function values inside of this set, which, by the way, is also going to be a compact set? If nothing else, then I could still say that the function values at, say, x equals 1/2, that these function values are still going to be inside of the original compact set where I was. And because that set is compact, there exists a further subsequence. We could go that say that this is true for each f sub n sub k. Then there's going to exist another subsequence in which this is now for kind of taking a look at these functions right here that we've drawn for f sub n sub k, that there's some subsequence of those that now continues to also have a point close by whatever this point is. Maybe I choose this one, maybe I choose this one. And again, notice that because that these two things are subsequences of the original sequence, they also have to converge at x equals 1. They're converging at x equals 1/2 and at x equals 1 here. And they're just going to keep doing that. Again, all of these things are happening within some sort of epsilon between each of these points. But if we push farther down the sequence, we can make those epsilons as small as we would like. So we repeat the process with x equals 1/2. And just to spell that out here, to say what that is, note that f sub n sub k of x equals 1/2 is a sequence, of real numbers, once again, contained in -1 to 1. This is a compact set, so there exists a further subsequence, f sub n sub k, and we have to give it another kind of sub-index here, sub L here, of functions. This is a subsequence of f sub n sub k, such that the values of, how did we write it? Such that the numbers of f sub n sub k sub L of 1/2 converges. And this is again by definition of, how did I write it up here? Compactness of -1 to 1. What's neat about this is that you might see that this argument can now be repeated several times over. In fact, this can be repeated at any point that I would like. If I see that there is a point in which my subsequence values are very far apart at one particular place, then I can say, okay, well, I'm going to repeat the argument again and ask that past a certain cutoff point, these things converge, that these are within epsilon of these values. Now, when you start throwing in all of these epsilons and stuff, it does get a little bit dicey. I talk a little bit more about some of the details of the epsilon back in my 6.1.4 video lecture video. But instead, what I want to focus on is where the diagonalization comes in. Because what we're doing here is we are constructing a sequence f sub 1 through f sub 5. This is the original given sequence. And our construction is allowing us to now take subsequences of that. So f sub n1, f sub n2, f sub n3, f sub n4, f sub n5, where this sequence converges, or rather has the property that f sub n sub k of 1 converges. That eventually, past a certain point, past a certain epsilon value, that we can get to that point. Then we can do the same thing for f sub n k1, f sub n k2, f sub n k3, f sub n k4, where these are the sequence elements that we were just talking about. And these have the property that f sub n sub k sub l of 1/2 converges. And because they are also a subsequence of the original one, we also know that f sub n sub k sub l of 1 converges. Because if you have a sequence converging, the subsequences, all this kind of selections of points that you might have, those also converge to the same point. And the idea is that we could continue. Maybe the next subsequence, we make two conditions. These have to converge at x equals 1/4 and at x equals 3/4 in the same sort of way. And at each of those steps, we can be making our epsilon values as small as we would want to. Right, we can say that these converge past a specific point, maybe when epsilon is less than. We talked about how this could be less than 1/4 and then less than 1/8. That eventually the ability for these functions to continue to get closer and closer to each other, that is, all of the y values are within this little window here, becomes very, very small when I consider what those y values are. That is, we can be setting those epsilon values to be smaller and smaller as we keep going and making more and more subsequences as well. But what we're thinking of here seems to be like taking a limit of subsequences. But here's the issue with just taking a limit of subsequences. Let's say that I start with the sequence 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. Then I can do a similar thing here to take a sequence, take subsequences and continue taking subsequences of those subsequences. For example, one famous subsequence of the sequence of natural numbers is that of the even numbers, 2, 4, 6, 8, 10. And I can take a further subsequence to be all of the multiples of 4, 4, 8, 12, 16, 20, 24. And then I can go even one step farther and take another subsequence, 8, 16, 24, 32, 40, 48, so on and so forth. And I can keep going. But you might start asking the question, if I keep taking all of these subsequences of sequences that were themselves subsequences, what's going to happen? At the end of this process, I'm not going to be left with any numbers. At even just the fourth subsequence, my least number is 8. My next one over is going to be 16. My next one after that, 32. And so every time that I make another subsequence, I'm doubling the first number in that subsequence. And you can see as I continue to make that limiting process happen, that past any point, I'm eventually going to have my very first element of this subsequence be beyond that point. So no number could be included in every single subsequence if I continue going on in this pattern, namely taking all of the things in the even spots of the subsequence that came before it. So for example, 4, 8, 12, 16, I'm taking everything inside the even spots to get to the first couple of elements for the next one and continuing on with that pattern. So I will never have anything inside of this limit of subsequences. But we get around that by using a trick called diagonalization. And you may remember us doing this a little bit when we talked about Cantor's theorem. When we were talking about particularly the uncountability of the real numbers, we said that one way to disprove that such a function was countable was to start making lists very much like this, and then changing elements along the diagonal. Now, here's what we're going to do. We're not going to change elements along the diagonal. We're actually going to choose elements along that diagonal, doing no changes at all. From the original sequence, I will take f sub 1. From the first subsequence, I'll take f sub n sub 2. From the next subsequence underneath, I will take the third element. From the sequence underneath that, I will take the fourth element, and I will continue this process all the way down as I continue making subsequences. And notice that what I get is itself a subsequence of the original set of functions. How do I know that? Everything that I have made here is a subsequence of these original functions, f sub 1, f sub 2, f sub 3, so on and so forth. So everything here lives amongst the original sequence. I'm also not mixing up any of my terms because the fact that this is a subsequence of this one means that if I'm choosing the third element here, then the farthest back or farthest forward in the sequence that that element can be in the original subsequence is just the third element of the original subsequence that I'm taking from. Basically saying that if this number is 10, then this number can't be 9, because this is saying that the second element in the subsequence of this sequence that I'm taking from above it, the smallest that this value could possibly be is 10. Because this is itself a subsequence, that means this number has to be at least 11. It has to go beyond what the previous indices were for previous parts in this function. So what I'm getting from all of this is itself a subsequence by our definitions of that. So notice that what happens with as I continue to go down the subsequence, our goal with each of this is to see that when I go and consider what's happening at each of these stages, I am continuing to, by our construction of these subsequences, have these functions converge at the original points and all previous points. I am also asking, because I can say that this will eventually converge for all epsilon, I can choose my epsilons to be as small as I would like to, as long as they're greater than 0, at each of these subsequences. So that essentially the y window at which these things can exist, the distance between these functions, continues to grow smaller and smaller and smaller, which looks a lot like it converging. The fact is that this is a sequence, this is a Cauchy subsequence of the original set of functions. This is a Cauchy subsequence. And I should say what this is, the subsequence circled in green is a Cauchy subsequence of the original sequence f sub n. And since the space of continuous functions from 0 to 1, since this is complete, this Cauchy sequence converges. Now remember what our goal was at the very beginning here. We started with the sequence f sub n, and we wanted to show that there was a subsequence of that sequence of functions f sub n, that converged inside of our set of contractions that started at f of 0 equals 0. And now we see that that is actually the case. We found a subsequence that converged. That is the Cauchy subsequence that we just found, as we've shown, and that each of the distances between functions here, the window between y values at any point here in this function, is going to be very, very limited in how far they could grow apart. So that gets us what we're looking for as far as finding something that converges. The last thing that we would want to do, we still have not shown the limit of this subsequence is itself in the set that we're working with. So that is the limit f must be itself a contraction such that f sub 0 is equal to 0. But this actually ends up being true as well for a few reasons. One, we have that the subsequence, which we might call f sub n prime, converging to f. Let f sub n prime be our Cauchy subsequence, and f be its limit. We know that this function f is a continuous function, first of all, because the uniform limit, and that's exactly the convergence that the continuous functions gives, that the uniform limit of f sub n prime to f, that this gives us that f is continuous. So f is a continuous function here. Is it a contraction? In fact, there's another theorem that tells us that we can now go through and take derivatives of the functions of these s sub n and get a convergence in the form of its derivative. So in fact, if you take the derivatives of these functions f sub n prime, which I have mistakenly called it this subsequence, I should have called it something else. Maybe I'll go back and change it briefly so that I'm not confusing the prime and what I'm using to denote the subsequence, so that the derivatives of the functions tilde f sub n, which are f sub n prime tilde, these guys, also converge to f prime. And this is by a theorem utilizing differentiability of the sequences f sub n together with uniform convergence. The meanings and the reasonings behind this type of theorem are very similar to what we saw back in section video lecture 6-2 for how that sort of thing goes. So the derivatives of these f sub n also converge to f prime, and since we actually know what these derivatives are bounded by, that these are bounded by values in between -1 and 1, we actually have that f prime of x is less than or equal to 1 for all x inside of our domain. Which means, so by definition, f is in S because it is a contraction such that because all of the original sequence values for this Cauchy subsequence, since they were all 0 at x equals 0, the function that they all have to converge to has to have exactly the same y value at x equals 0. So we are done. And that gets us our little box, our little happy face. And what I'm hoping that this did was help you see a little bit more as to what this diagonalization argument is all about. Now, in the video, I will say something that I'll emphasize again, which is that our goal is not to have to go through this argument every single time that we want to show that a set of the continuous functions is compact, because there's a lot that you have to think about in order to make these types of theorems work. There's a theorem that we're going to talk about this week called the Arzela-Ascoli theorem that says you don't actually have to go through this argument every single time. You only have to check a few things, one of which is equicontinuity. Equicontinuity is something that we're going to be needing as we start moving forward into here, as we start analyzing a bit more about compact sets. So that's the reason behind and the motivation of defining this word for us as we move forward. But what I'm hoping that this did was give you a little bit more into what the diagonalization argument is all about and see a little bit into how we can start showing that certain sets are compact as we move through here. But that'll do it for me today. Thank you so much. Have a wonderful day.